This is the first in a series of A-level mechanics videos, and as promised to a few of my students, this topic is going to be on the statics of rigid bodies and a hinge problem. So the first thing I want to do is to read to understand this problem. Right, so we're told that we have a uniform rod, AB. So this is A over here, B over here. This is the rod, AB, of length 2A, which is provided, and of mass M, which is smoothly hinged at the point A, which lies on a vertical wall. Okay, this means that we are looking at this from the side. This is a side elevation. So this is the vertical wall, and this direction is upwards. The rod is kept in a horizontal position by a light inextensible string, which is BC. Okay, so B to C, where C lies on the same wall vertically above A. We're then told that the plane ABC is perpendicular to the wall and the angle ABC is denoted by theta. The plane ABC being perpendicular to the wall means that when we look at this in plan, so if this is the wall, so we're looking at this from above, this is the uniform rod, this is the point A that's on the wall, this is the point B, that's the other end of the rod. The angle between the wall and the rod is a right angle. So we're then told that tan theta equals a half. We're then asked to show that the tension in the string is a half √5 mg. So we'll start with that. So the first thing I'm going to do now is I'm going to put on the forces. We're told that this is a uniform rod, which means that its mass M is at its center. So its weight here is going vertically downwards, and it's right at the center. So the distance here is A. The next thing I'm going to do is add on the tension, and the final thing is to add on the reaction at the hinge. I've split this into two components, a vertical component and a horizontal component, but we must include these in this style of problem. As the first task is to find the tension, what I want to do is perform an action that is going to eliminate as many variables as possible in one go, and this action will be taking moments about A. I've chosen to take moments because when I take moments about A, the reaction, the vertical reaction and the horizontal reaction, both go through A. The line of action of their forces both go through A as they're centered at A. This means when I take moments, their effect will be 0 and they'll be eliminated. So the only two forces that I'll have to deal with will be tension and weight. So I set out my notation. I'm going to take moments about A in a clockwise direction. When we're taking moments, we must have the dimensions, and we must have the perpendicular distance to the line of action of the force. I have this for the weight. That's a distance of A away from A. That's little a. I have this for the weight because this is a distance of little a from capital A. But I don't have the distance of the tension, the line of action of the tension, from A. So for this, I'm going to have to do some geometry. I know that tan theta equals a half. So I'm going to draw a little right angled triangle to denote this. Then put the opposite is 1. Adjacent is 2. So that gives me tan theta equals a half, which gives the hypotenuse as square root of 5. This means that sine theta equals 1 over √5 and cos theta equals 2 over √5. So I'm going to use these in my calculations. So back to my calculations. Moments about A. The weight is a distance of A away from capital A. That's the perpendicular distance. So we get mga clockwise. Now the distance of the tension. So we've got to get the perpendicular distance. And as we can see, this is going to be 2a sine theta. So the moment about A is going to be minus t times 2a sine theta. And the sum of these moments, because it's in equilibrium, is going to be 0. So I'm going to cancel the a's and rearrange. 2t sine theta equals mg. Sine theta is 1 over root 5. And finally rearranging, we get t equals a half root 5 mg as required. The second part of the question is asking us to find the magnitude of the reaction at the hinge and show that that is the same magnitude as the tension in the string. So for this, we're going to need to use F equals ma, so Newton's second law, and we're going to need to resolve both vertically and horizontally. So resolving vertically first and using the correct notation, we're going to get as follows: RV plus t sine theta minus mg equals 0. So the vertical component of the reaction at the hinge equals mg minus t sine theta, which cancels to give me half mg. Resolving horizontally, we get RH equals t cos theta. So that means that equals a half root 5 mg multiplied by 2 over root 5, which cancels to give just mg. So then combining my two components, horizontal and vertical, we've got horizontal is mg, vertical is a half mg. When we find the resultant of these, we need to square, add and square root. So the overall reaction at the hinge equals mg squared plus a half mg all squared, all square rooted, which then simplifies to give the square root of 5 over 4 m squared g squared, which gives me, when we finally square root that, half root 5 mg, which is the same magnitude as the tension in the string. I hope you enjoyed that video. If you want to see similar videos to this, then please comment and please tell me which topics you'd like me to cover. Thanks a lot there.